We are going to look at a second example for putting it all together, and this one is going to be a bit more complicated than the first one. So I wanted to separate the videos so that you could see a simple problem that was put together and a more difficult one. So for our more difficult problem, we are heating liquid butane. Well, when heated, liquid butane reacts with oxygen gas to produce carbon dioxide gas and water. Okay, so again, butane, we don't know what that is. However, the problem told us what that was because that isn't one of those names we have to memorize, and you're not going to find it on either the periodic table or polyatomic ion chart. Reacts with oxygen gas to produce carbon dioxide and water. Okay, so all of those things can be found on the periodic table. So we're going to use the periodic table. Again, sometimes you will need the polyatomic ion chart, but for this example, we don't. So liquid butane, we're going to go ahead and write that. C4H10, and it's a liquid, reacts with oxygen gas. Reacts with, okay, oxygen gas. Oxygen gas is here. Oxygen is here. But it's one of those 7 diatomic elements, and I'll go ahead and indicate this again in case you have forgotten. The 7 diatomic elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So Brinkelhoff, Brinclhof. Those are our 7. Okay, reacts with oxygen gas. So that's O2 to produce carbon dioxide. Oh, we have a prefix, so we know this is covalent. Carbon is C, oxide is O, di indicates 2, so this would be carbon dioxide gas, and water. Y'all all know water. It's H2O, and it says and, so we know we need a plus sign. Notice I wrote an L after it, even though up here it doesn't say liquid water, but we can figure this out because the problem indicated water. If it had been solid H2O, it would have said ice, and if it had been vaporized H2O, it would have said steam. Now, we have to go back and balance this equation, and balancing an equation like this can be quite difficult. So before we go any further, I want to go ahead and indicate the type of reaction that we're working with. Well, I have a CH, so here, this is a hydrocarbon, reacting with oxygen gas to produce carbon dioxide and water. So we know this is combustion. And as a heads up, combustion reactions are generally more difficult to balance than the other types of equations. So let's look at the different elements we have. We have a C, an H, and an O. A C, an H, and an O. So let's go ahead and write those down. C, H, O. We have the reactant side, we have the product side. First things first, we need to count the number of each on the reactant side and then do the same for the product side. So C4 is our reactant side. And over here on the product side, I only have 1 carbon. Hydrogen. Here I see 10 hydrogens. Ooh, we've already got big numbers. And over on the product side, I only have 2. And then oxygen. Here on the reactant side, I have 2. And on the product side, and don't forget this, oxygen is both here and over here. We must add them together. So we have 2 oxygens from CO2 and 1 from water. That makes 3. All right, so we see that this is going to be a little more complicated. But when you're doing balancing for a combustion reaction, let's start with the carbons, move to hydrogens, and save the oxygens for last because the oxygens have been split apart into 2 different compounds. So to balance the carbons, this one should be pretty easy. I have 4 and 1, so we can just add a 4 out here because 1 times 4 is 4. But note that when I do that, I've also changed the number of oxygens. So now I have 4 times 2, which is 8, plus this 1. That's 9 oxygens. 9 oxygens. I am so sorry. Okay, let's do hydrogen next. So H, I have 10. So if I go over here and look at my section with the H's, with the hydrogens, How would I make a 2 equal 10? I have to multiply it by something. Well, 2 times 5, so 5 times 2 is 10. So I'm going to multiply that by 5. Again, when I do that, I've also changed this oxygen over here. So now I have 5 oxygens from the water and 8 from the CO2, which means 8 plus 5, that's 13 oxygens over on this side. I only have 2 on the reactant side. Now, we found ourselves in a bit of a dilemma because there is no number we can put here. There's no whole number we can put here that would allow us to multiply by 2 and get to 13. So here's the trick. We are going to multiply this by the decimal number. So 13 divided by 2 would be 6.5. So let's go ahead and write 6.5 right here. But we know that we can't have half of an oxygen molecule. It's there or it's not. So we can't keep this, but this is going to help us for right now. Okay. So yes, everything's equal right now, but we cannot leave a decimal as a coefficient. So what we're going to do is go back and multiply all the coefficients by 2. Multiply all the coefficients by 2. So here we have a 1. So 1 times 2 is 2. Okay, we have 6.5. We don't want that anymore. So 6.5 times 2 is 13. 4 times 2 is 8. And 5 times 2 is 13. I'm sorry, 5 times 2 is 10. So let's check to see if this worked. And I'm going to go back and erase some of this other stuff so that we're not distracted from what's happening. So let's see if it makes sense and if everything is balanced now. If not, we can always go back and do more. So starting here with this first part, we have 2 times 4, which is 8. So that's 8 carbons. And here we see another 8 carbons. That's good. Okay, now we have 2 times 10. That's 20. And over here we have 10 times 2, which is also 20. Okay, 13 times 2. That's 26. And finally, so we have them split up. We have to add 8 times 2 is 16. So that's 16 plus 10. That's 26. So we have 8 carbons, 20 hydrogens, and 26 oxygens on each side of the equation. And that is how you would balance a combustion reaction. So the trick here is to go ahead and put that decimal number in for the oxygen, but then go back and multiply all the coefficients by 2.